We have 9 faculty members in our department now. So we are already, struggling to started our independent research career. So with in aim of getting some of the, motivations, the how research can be pursued, because all of you also started, research when ICER was almost just started, right? So there is nothing in place too. So, and then you're able to excel in your area. So that's going to give us an idea that what cutting edge research going on in this direction. So without further delay, before going to start, I like to invite our Associate Dean of Science, Professor Ranjit Thapa is here to give some, opening remarks about this faculty development program. Professor Ranjit Thapa.
Yeah, Dr. Nimai, thank you very much. But I don't know that I have to give the opening remarks. Just I think without delay we can start. I really appreciate the effort from Dr. Nimai and Dr. Satish. And of course, Dr. Nimai was always have done a lot of events and other things. Always he involved in that. And I hope Satish will take his legacy in future. And because it's very important to connect with the different researcher within India and also abroad, and listen to them how they are doing different research in their respective area, and we can learn from them. And with this, I want to welcome Professor C. Malla Reddy and Professor Srinivas Hota, and to deliver the lecture. We are eager to hear from you. I think everyone wants that. So over to you, Nimai.
Yeah. Okay. Thank you so much, Professor Thapa, for your kind words. And now I'm going to hand over to my colleague, Dr. Satish Ilipalli. So he will take over the session. Satish, over to you.
Yeah, sure. First of all, thank you very much, Professor Srinivas Hota, for accepting our request for the deliver the talk at for the program of faculty development program. So I would like to introduce Professor Srinivas Hota. He's going to deliver his talk first. It's my privilege to introduce Professor Srinivas Hota. He completed his BSc from Andhra University and MSc from Hyderabad Central University. So then he did one more master's course, MTech, from Benares Hindu University. Then onwards, he did PhD from Osmani University while working at National Chemical Laboratory, NCL, and Indian Institute of Chemical Technology, IICT Hyderabad. And then he did a postdoc with the Professor Taran Kapoor, Rockefeller University, New York. And once he completed postdoc, he joined National Chemical Laboratory, NCL, as a scientist. Then he moved to ICER Pune, which is next to the NCL, where he is currently working as a professor of chemistry. He's a recipient of Young Scientist Award from INSA, Indian National Science Academy. And he's also won the prestigious DST Swarna Jayanti Fellowship in 2010 for his outstanding contribution in the field of carbohydrate chemistry, particularly for the development of gold catalyzed glycosylation. And he published his work in various prestigious journals. Some I'm giving here, such as like Nature Communications, Angewandte Kime, JAX, Chemical Science, Langmuir, etc. So he has done immense contribution to the field of carbohydrate chemistry. So with this, I would like to invite Professor Srinivas Hota to enlighten our faculty and students. So today's his talk title is Discovery and Development of Gold Catalyzed Glycosylation for the Synthesis of Oligosaccharides.
Would you enable me to share my screen?
Mm-hmm.
Sure.
Okay.
Yeah. Can you, I request our support staff to make him co-host, both the speaker, Professor Malla Reddy and Professor Srinivas Hota.
No, I can't share yet.
Just 1 second, sir.
One second.
Let me call them. They are here only. Just one important announcement for all these attendants. You can raise your hand at the end. Then we can allow you to ask your questions directly, or you can put in the chat box. Both are okay. So just let me call this person.
While the slides are getting projected and all, I would like to thank Satish for inviting me to this interesting online seminar. And it's a great privilege to talk in front of one of the greatest scientists in the contemporary India, Professor C. Malareddy. And at the same time, I don't know whether I'll be able to, I mean, I'm taking his time and all of your time. So I hope I'll be able to impress upon you whatever little small thing that we do in our lab. At the same time, now I can actually share.
Yeah.
And I shall thank once again the Nimai Mishra for the invitation and hosting me. And I will once again thank Satish for sending the reminder email 5 minutes back. I was thinking that the meeting is, for whatever reason, I mean, I thought that the meeting is going to be tomorrow, but it happens to be today. So in 5 minutes, I cooked up something. So if I'm unable to connect, please forgive me. And as usual, if you see this slide, most of the work is not done by me. And it has been done by my students who seems to be enjoying that, but not seriously. This picture shows that there is one guy who is completely lost in the whole process. So that's me. I'm only presenting this one, whereas the whole work is done by these guys who are excellent. And then I sincerely thank them for doing the hard work and enabling me to give this talk. Okay, so to introduce what we do can be classified into two different things. One is we develop methods for glycosciences, and I'll touch upon these things at some point of time during the presentation. And we also have yet another thing that happens in the lab is we develop some tools for the society. For example, mosquito repellent, which is completely away from whatever the glycoscience that we do. What we do in this one, there is a remote connectivity to that one, except that the carton is nothing but a simple polysaccharide, which happens to be cellulose. And then we modify that with a known mosquito repellent, and then we look at their long-lasting release and then all such kind of things. The second thing is that we have created something called some tools for people to learn whether it is organic chemistry or it is a periodic table of elements, or maybe at some point of time we did that, but now we stopped doing that one. These cards we have created, and then I ask students to play in the class so that they can update their knowledge about organic synthesis and reagents especially. These cards are quite useful for students who write the CSIR JRF NET exam, especially with organic specialization. And then today I will be going to talk a little more about this particular life-saving track. Okay, having said that, what's all this glycosylation is about? It is about the activation of this particular LG, which is present here. Once that departs from the glycan moiety, then it generates an oxocarbenium ion, which will be able, which is available for the attack of the aglycone either from the alpha phase of it or beta phase of it, depending on what are the constituents or what are the attachments which are present on the glycan. And accordingly, we can get a disaccharide if we are using it as a glycone is a saccharide. Okay, why we are concerned with this one is they are present in many forms, and life without these saccharides is not possible. And at the same time, they are constituents, there is conformational advantages, and then they are deferred by connections. They have configurational problems, and then they have a variety of substitutions on these OP and OP. Depending on the substitutions, also species gets differentiated. And at the same time, if we look at the desirable properties for this kind of activation procedure is that this particular glycosyl donor needs to be stable so that you will be able to use it as and when you require. And it should be scalable, and then we should be able to use stoichiometric quantities, and then it should be a safe reagent, and then if possible, we should have stereoselectivity in the resulting glycoside that is forming. So way back in 2006, because of some observations, we found that if we add a AU3 salt to a propargyloxy glycoside, then we will be able to activate the alkyne group here, and then using the AU3 salt, and then we could generate the oxycarbenium ion, and then we trapped that one at 65 degrees Celsius, and then using variety of glycons. But the problems that happened is, one is the high temperature, and at the same time AuCl3 being in the presence of alcohol will be releasing 3 molar equivalents of HCl, so that started cleaving off this intraglycosidic bond. And later on, what we did is that we made a library of different attachments as leaving groups. And we try to reduce the temperature from 65 degrees to room temperature or sub-zero or 0 degrees Celsius, so that with a wishful thinking that we shall be able to arrest the cleavage of this interglycosidic bond. But that did not happen even when we reduced the temperature from 65 to by doing variety of different substitutions here. And later on, what we also have done is that in that context of reducing the temperature and increasing the reactivity and stereoselectivity issues, we trapped 1,2 as this kind of an orthoester, which upon extrusion of this propargyloxy, propargyl alcohol, will be generating a carbocation here, and then that will be delocalized in this as a trioxylenium ion. And thereby it will be able to give me now 2 things. One is that at room temperature activation. And the second thing is, because this side of the molecule is locked, so now the incoming nucleophile comes from the beta phase of it, so that it becomes a 1,2 trans glycoside. But quite recently, after almost 10 years later, so what we did, we clubbed many of the things which are existing in the literature, and ultimately we found that if you can have a carbonate, then one can go the temperature nowadays we do up to minus 78 degrees Celsius. So why this temperature makes a big difference is because the glycoside formation, though I wrote it in the forward arrow, actually it's an equilibrium. Okay, so it leads to, once it is in equilibrium, we all know that it leads to thermodynamic and kinetic effects. So if we want to get 1,2 trans, it is our more sterically demanding thing, it's always better to go for the kinetic product or less reactive things, and then we reduce the temperature. So when we do it at lower temperatures, then we normally get the alpha glycoside more, and then when it is a higher temperature, we get 1,2 trans more, or which is beta isomer in the case of glucose. So there were others who followed our work from 2006 successively, and then it's like a race between you and me, and then like it went ahead, and then we tried to improve upon, and then they also tried to improve upon our results, and then we tried to use their results, and then we tried to improve, and then it's a race. So in all this one, what we did is that we developed several stable glycosyl donors, and then these are all catalytic quantities. If you see 3 mole% to 8 mole%, and noble metal salt, so that means that it's less toxic, and then these have longer shelf life. More importantly, this particular one, the quite recent one, carbonates, are majority of them are becoming like solids. I mean, it's a stupid thing to work around the syrups because they cannot be transported easily. Whereas if it is a free-flowing solid, one will be able to transport the molecule much easier, and then one can actually look at the prospect of selling it at some point of time if somebody is interested. And then these are all amenable for scale up 2. So having said that, what we did with these protocols, we can make nucleosides, N-glycosides, amino acid glycoconjugates, aryl glycosides, C glycosides, whatever that you can think about, we can do that. At that point of time, the question that we asked ourselves is, how our donors will be performing with reference to the oligosaccharide synthesis. Why this is such an important task is, majority of the glycosyl donors, actually what happens is, if you want to make a simple glycoside, there are more than 50 different glycosyl donors which are available in the literature. But if you increase your boundary condition to something like synthesis of a trisaccharide, it reduces to maybe 20. When if it goes beyond 10, it reduces to 5. And if it happens like above 10, then there are now, at this point of time, there are only 3 of them. One of them is our donor. and the other one is thiotol, and the third one is a phosphate donor. Only these are the three donors which are available for anybody and everybody to synthesize larger oligosaccharides. So the model system that we have taken is Mycobacterium cell wall, because the reason is pretty simple, because its cell wall is completely decoded way back in 1980s by Patrick Brennan, and at the same time, it's not too many carbohydrate epitopes are completely decoded. So one of the model cases is this Mycobacterial cell wall saccharides. Okay, so if you look at the whole picture about this is done about a year back. So if you look at this 2017, Seeberger has done a 50 more using his glyconeer machine. Later on, he also has increased the number to 135 or something. But the problem with that one is not problem, but one of the limitations of that particular thing is that he added only manos. Okay. And whereas this guy from China, he has done in 2017, soon after our paper in 2017, about arabinogalactan, that it's a 92 mer, which contains many branching points, and then it's a very important one for many of us to think about. Okay, and later on this number has been improved to 151, but still the for me, for whatever reason, the personal record is this particular one, because it's much more complex compared to what this particular machine has done. From my lab, we could do what is the published number is 25. We had the record for a brief period of time, and then later on this Chinese group has taken over for that. So as I said, this particular picture shows you that whatever MTB, there is arabinogalactan, lipoarabinogalactan, glycoprotein, halos, and then a lot of things are there. And this is the inner membrane, outer membrane, and there's so many things in terms of the biology. But why we wanted to, we are concerned about it is, we wanted to see how to synthesize this portion of it, because the structure happens to be as like this, which has got 131 residues. I'll show you the complete structure a little later. And there is another one which is lipoarabinomannan. We have already completed the synthesis of this 51 sugar residues which have been attached to each other. Still the manuscript is not published yet, but this one is part of this one is published, and then we are trying to address the 131 sugar residues. Okay, so this is the structure of that 131 one. If you look at, I mean, you do not count, actually there are 131 residues. I think my students have done a great job of counting how many number of sugars are there, and to synthesize such kind of a complex oligosaccharide, what we required were only two methods, one for the 1,2-trans and the other one is 1,2-cis. And at the same time, we also require a method to make this particular rhamno derivative and then glucanac. And for that one, we have developed a methodology where we can convert a pentenyl glycoside into a carbonate, so that this one will not be getting disturbed during the course of the reaction. So this can be converted into orthoester, or this can be converted into the carbonate. Okay. So that means that if you look at the history of this particular molecule of 131 mer, the whole story started in 1996 with a good paper by Gurjar, and then several other people have worked on different fragments. So for almost like a decade or something, as carbohydrate chemists, we learned the art and craft of making these small pieces. At that particular point of time, making a hexamer or a pentasaccharide is quite a lot. And as the decade progressed, then Lowry has published this particular small piece from there. And then what we did is that, can we do that one? And then we did all these small pieces coming from one side or the other. But so how did we do that one? It's not that we did in a simpler manner. I'm going to demonstrate you such kind of things with examples. So for example, if you want to make the piece that I'm talking about, this particular one, so it requires the use of one glycosyl donor and an acceptor. And then once you activate this one, then it becomes oxocarbenium ion, and then we'll be able to trap, and then ultimately we'll be able to get a disaccharide. Now this disaccharide is strategically positioned because the TBDPS group can be deprotected using HF pyridine to get you a disaccharide which can act as an aglycone, or one can actually deprotect this allyl group, so that now what will happen, a hemiacetal will come that can be converted into the carbonate, so that now it became the donor. So now what we did, we clubbed these two to get the tetrasaccharide. Now you can do the same thing. So split pool or split react and then convert, so that we will be able to make the 19 or known as decasaccharide 19 mer in a very easy fashion. So we call this as split react couple strategy. So for example, in this one also we did a similar thing where, I mean, this is true for the linear one. Now you'll ask, what will happen if I have a branching position? So now you take the same thing with a diol, and then we'll be able to get the trisaccharide, and then you deprotect on one side to get the diol and convert this pentenyl group into the hemiacetal followed by carbonate, so that we'll be able to get the carbonate, and then we couple both of them to get the nonasaccharide, and then if you treat with 5.5 equivalents of this particular donor, we will be able to get the 13 mer. Okay, this whole exercise required us about 10 to 12 synthetic steps, 14 steps for the 13 mer, including the synthesis of the monomers. And if you look at the reactions are pretty steady. I mean, this is the donor and this is the acceptor, and then ultimately we get the product here. And in this case, this is the product, and in this case, if you see, the product is here. Okay. So this is what we said that, okay, split react couple. Now I demonstrated to you that this is a beneficial one, so that we'll be able to achieve the targets in a much easier fashion. So having said that, now I required a method for me to make 1,2 transglycosides. How do we make? So we thought of using this orthoester strategy, so that the orthoester, once it is formed, this side of the oxocarbenium ion will be, sterically demanding. So because of the neighboring group participation, and then the aglycone will be able to come from the alpha phase of it, or 1,2 trans phase of it, so that we now will be able to get 1,2 trans. Now you may say that you are getting 2 compounds, but this particular one has a much higher, the polarity difference between these 2 molecules is very high, because of which the column chromatography becomes very easy. Okay, at that particular point of time, we demonstrated a variety of different substrates. So the problem of 1,2 trans selectivity more or less is stabilized. And then after that, now we require yet another method for making 1,2 cis glycosides, which are nothing but 1 and 2, and then they are cis to each other, or S-syn to each other. Okay. So how the nature does it is, it does not start from the arabinose in the furanocil form. What it does is that it takes ribofuranol, and then it uses 2 enzymes which are now probed by these people as drug targets. In the presence of some cofactors and all, it gets oxidized to Ulose derivative. And once you reduce it at another sodium NADH and NAD+, so you get inversion here, so that oxidation and reduction is one of the popular methods. Long ago, actually, Robert Field also have demonstrated and highly substituted this kind of a system where he oxidized and reduced to take it inversion. So what we thought is that since if we start with ribofuranosyl orthoester, then we shall be able to get this particular C2 benzoate, which upon saponification, we should get the alcohol. And then oxidation followed by reduction, we could successfully demonstrate using a variety of different analytical tools that one can actually get 1,2 trans in a very easy fashion. Or 1,2 cis in a, sorry to say that, 1,2 cis in a very stereo controlled fashion. So this gave us a clue. And the third methodology that we required was to convert the pentenyl glycoside into an orthoester. Why is it required is that in terms of, you will realize that in a few minutes. So this, when you do the synthesis, so you require to make a disaccharide. Earlier, I have shown you allyl group. Instead of that one, if I put pentenyl, then it gets much easier for me to activate the pentenyl group in the presence of idonium ions, so that I'll be able to make the or even I can also make a bromide from here, which is not possible with the allyl glycoside. And we shall be able to get this particular thing. If at all that is not working, then I can go back to AuCl3 and then pentenyl alcohol. I'll be able to get the starting material back. Okay, with that wishful thinking, once I have the method for 1,2 cis and 1,2 trans, and then whatever the remaining things, what we did is we thought that, okay, let's target this particular one, which is less complicated because this has 1,2 cis derivatives also here at the terminal end of it. Whereas the next molecule, we thought that initially we'll make only with this one, which has got all the trans linkages in this. So there are about I mean, whatever the number, 19 arabinose residues, and then 2 galactose in the furanosyl form, which is not present in humans or anywhere else. So this biosynthesis of this particular linkage is again probed by a variety of medicinal chemists for the development of the drug. They are now trying to find efficacy of that using some of the substrates which were possible through this synthesis. So what we thought was, let's break the point at this one so that it becomes 2 molar equivalents of this tetrasaccharide followed by this kind of a long oligomer, and which again can be realized from this trisaccharide, tetrasaccharide, and then this heptasaccharide or hexasaccharide and then tetrasaccharide. So we call them as cassets, and ultimately it boils down to a situation where you require to use these 6 building blocks so that you will be able to realize the molecule in an easier fashion. So once that is done, then what is the next thing is my students have worked hard for almost like 5 years or 6 years to make some 1 or 2 milligrams of this particular compound in about 47 steps with 0.09 or 90 milli% yield with 21 stereoselective glycosylations. But for us, the most important thing is that all the glycosylations were done by an in-house method, which is nothing but gold catalyzed activation of the orthoesters. Okay. So having said that, now what's the next thing in the series? So we wanted to now, if you see this particular molecule by synthesizing, we put acetates here. So we thought that we'll remove these acetates and then proceed further. That has become a big task for us. Because when we did the deacetylation of acetate using all the known methods, sometimes we started seeing that one of the benzoates is not getting off and one of the benzoates is also cleaning off. That became a big task for us to find out which particular benzoate is losing. So, and at the same time, then we completely changed the route and then made PMB in all these 4 positions. Again, some other problem came. And ultimately, we abandoned this entire route because the whole thing boils down to how to deproduct this PMB group from there. Okay. So now, having said that, now where is the mistake in this whole synthesis plan? How to get this material? So now, what the original retrosynthetic plan is, we thought that we'll take 2 hexasaccharides, 2 molar equivalents of hexasaccharide to get the 12 mer, and that we wanted to couple it with the 13 mer to get the 25 mer. Why did we do that one? What we have successfully done that one is that 2 times 4 is equal to 8 mer, and then that we coupled to 13 mer, so that 21 mer we could make it and we could publish it. Having said that, now what we have understood, one thing is that if it is becoming a difficult task for us to remove that PMB group from there and doing into the hell lot of cycles, so instead of that one, we thought that we'll remove 1 from here so that it becomes 2 into 5 is equal to 12. And those 2 residues can be added onto this side. So it becomes a 15 mer. So then I'll show you what is the advantage of that one is that now we got a much better control on that one. This pentasaccharide has become a pentasaccharide here. And this disaccharide has become now a repeating unit. And then we have a trisaccharide, which is shown in the green color. And for us, the remaining things were, by then we discovered this carbonate donor also. And then we are also having the oxidation reduction method. Everything is in place for that one. So what's the advantage of this route over the previous one? The reason is long back in 1995, the original isolation or whatever, those guys have said that these are the major motifs of Mycobacterium tuberculosis. But through the mass spec studies. But why did we consider this route is because we got carried away by the literature reports, which suggested that the hexasaccharide, what they did is that when the first paper came out to be a pentasaccharide as a motif A, then later on to become first, what those guys did is that they added 1 more sugar residue there and said that actually that is the hexasaccharide motif. And then people started getting carried away, and we also get carried away by that hexasaccharide versus pentasaccharide debate. And ultimately, we realized that if we do this way, then it's much easier for us to couple this one. And ultimately, we achieved this in about 77 steps with 1.2 milli% yield. And again, everything is from our lab protocols, and it was pretty successful. And then we could get fully protected mass spec, and then we could prove the structure unambiguously by putting proton frequency more of the deprotected ones, and then we were pretty much happy for that. Okay, so now what's the next? So how do we make this 131 sugar residues? These two guys have thought that we'll make, but they also failed. Almost like this is the third generation of people who work. And then this fellow is now in Sinjin, and then he is now a postdoc in some Boston area. And then we revised the scheme, and then we made up these materials, and then we tried to couple them. Right now, at this particular point of time, 131 for making. There are yet another students. This is the fourth generation of people who have joined. These two guys have shared the molecule. So one is now building up the material for this entire 31 sugar residues, and the other one is actually doing this the remaining portion, so that we should be able to couple them again and again, so that we shall be able to, at some point of time, these two guys are pretty confident that they want to make this 131 mark. Let's hope that we will be able to show you that particular data at some point of time. But to summarize what we have done, it is due to some accidental discovery of a bottle of AuCl3 in the lab, we started, and then ultimately we could generate an impact to this particular science by showing variety of glycosyl donors, and then we could achieve 25 mar. And then today, the next question is, now we got this one into the round bottom flask worked, and then we could get the molecule. Now, many people think that, okay, now why this particular statement is important is because the glycosaminoglycans are very important. One of the most important molecules, which is listed here, is called as fondaparinux. So this was in great demand during the Corona times as well. And this is also a heparin family's thing. And then there were a lot of people who worked on this one, have decoded and then said that there are two antithrombin sites, and then this actually intercalates between our forms a dimeric start or whatever. But at the end of it, they have found that this particular pentasaccharide is responsible for the antithrombin binding activity of whatever. It does not let this kind of a complex to form. Okay, so these are the two individuals who are responsible for identifying this molecule. By reductionist approach, they have fragmented that heparin and then tried to see where the activity is, and ultimately they found that this particular molecule, which is a pentasaccharide, contains glucosamine, glucuronic acid, uronic acid, and glucosamine. And more importantly, this particular sulfation here makes it to be 10,000 times more potent compared to the original molecule that they have. So this is the full the thrombin domain, this is the antithrombin domain. Whatever that one, do not get carried away by that. So the problems that happen to be are, there is a uronic acid. So there are a lot of reports which said that you can get the uronic acid as the late stage oxidation. You complete the synthesis and then put a orthogonal protecting group and then convert, oxidize using a tempo or something, so that we will be able to get that one. But the problems are severe. So because the molecule is going to be like a hell lot of tasks, because you require to use multiple protecting groups in order to get one single sulfation group here. So what most of the researchers done is that they try to avoid synthesizing that. Okay, so we thought, can we use yet another strategy? Can we develop yet another strategy that will enable us to get this particular sulfate also, so that we will be able to make a scalable synthesis for that one? And this is to play with protecting groups, one would say that one, but it's not simple playing with the protecting groups, because anything that you change in one place, I'll show you with data that if you change one place, the reactivity also changes. Okay, so this is the summary of that one. I mean, I'll show you again this particular thing at some point of time during the presentation. So we scaled up to 10 gram scale of this particular molecule, and we could get a good one patent, one paper for 5 years, one PhD, one molecule, and all this. Okay. And that fellow has completely identified this particular route. Okay, so what we did is that we thought that, okay, now let's make a comprehensive route. Either we can make through this three units, and then we can make it through this, so that you will get 3+2 approach, or you make this one and then make these trisaccharides, so that you will get yet another way to make that. So either 3+2 strategy or 3+1+1 strategy. And then we identified common building blocks with so many variations in protecting groups. You will appreciate that one once I come to the next stage. So both can be achieved from D-glucose and D-glucosamine. And before that, we did not work with glucosamine because the AU salts normally get quenched by the amines which are present in the molecule. The first thing is how to make the entire discussion of majority of the people who are involved in the synthesis of this molecule were all stuck with the development of a new route for this simple building block, which is nothing but hydronic acid. Hydronic acid is nothing but if you have this carboxylic acid on the top or whatever, I don't know, it could be equatorial phase, then it actually becomes glucuronic acid. One can actually do, we thought that why can't we do by simple inversion of this, we failed, and then these are the literature reports which suggest that majority of the things are actually been, so initially we thought we will use Krapchow mechanism to do that, and then we failed miserably to, and we made all these different types of, we played with a lot of conditions, and then each one is like a frustrating thing for almost like some 1 year we spent on to develop this, but at the end of it, majority of the methods either were giving this one or not reacting at all. Okay, so which is again possible. I mean, there are a lot of reports which suggest that this elimination is possible because it has precarious, even the benzyloxy group can act at a leaving group. Okay, so then this is yet another one, and then we tried that one, we failed in that, and then we had a lot of things, and then we could get the crystal structure. You see, this is what is the PT for a what is that? Failed results also we get crystal structures, but for the result that is required, we did not get the crystal structure at all. Anyway, so then we thought we will use yet another method. So what we thought is that we will, why can't we use pH or a phenyl group as a surrogate for the carboxylic acid? So then we thought, okay, if this aldehyde is very easy to make from starting from glucose diacetylene. And then we did the phenyl magnesium bromide addition so that we could get the phenyl addition there, which can be converted into the pyranose. And then after that, whenever required, we can do this pH oxidation. But then there is benzyl group. So because of which now that also started getting oxidized and getting deprotected. Again, protection, then all those things are difficult. So we confirmed you whenever acetate is there, we can make this very conveniently. But if you want to make it with the benzyl group or any orthogonal protecting group, it became a difficult task. So then we thought, okay, instead of phenyl magnesium bromide, can we consider this thiophenyl? Okay. Not thiophenyl, but thiofuran based magnesium bromide or thionyl bromide. We treated magnesium to get thionyl magnesium bromide to get this particular isomer in greater than 10 to 1. And then when we did it at a much lower temperature, we could now get almost like a near quantitative yield with 100% stereo selectivity towards the EDOs. Once we have that one, then the rest of the steps are straightforward. We could make with benzyl and then 2 acetates here. So having got that one, then we converted that one, and then we could then put benzyl. See, this beauty of this particular molecule is now these are all orthogonally activatable or cleavable groups. I mean, methyl, benzyl, TBS, acetate, and then this one is for the glycosylation. Okay, so then the next task has become like, how do we get this alpha selectivity? Okay, so that is yet another problem. To address that one, we started with anatrog and then converted that one into so many things, and then we made all these derivatives. Why? Because any change in one of the function, one of the protecting groups will be having a deterrent effect on the other one. It's a cascade effect. So similarly, we also made a lot of these glucuronic acid derivatives, and ultimately we started looking for how to make this particular disaccharide in a stereoselective fashion. You see the problem here. You have the leaving group, which is nothing but a carbonate. Okay, and then we add AU, AG salts at whatever the ratios, that 8 mole% each of this one. When we did this reaction, we did not see any kind of a stereo control on this with 4:1. Should we be happy or should we be unhappy? The reason is we got the product, but 4:1 inseparable mixture. Okay, so we could not separate them unless and until we remove one of the protecting groups, we cannot separate. Then we thought, okay, now let's put anyway, we have a library of these compounds. We thought that, okay, let's screen them. And at 25 degrees, 4:1, but that guy, out of frustration or whatever reason, he reduced the temperature to minus 20 degrees centigrade. He saw it to be 8:1. And when he went, but the problem is, again, this mixture that is happening to be is an inseparable mixture. Okay, so the best he could get is 8:1. Okay, so then what he did is that he went further down using these particular functional groups, And then he could get at minus 40, 20 to 1. But still, it's not separable. So I either have to remove the benzoate or TBDPS in order to get the separation. So which is again a nonsense thing. So, but we went ahead and continued and converted that one. But when we did this, somehow we spent 1 year to establish this particular one. And after that, 2 steps went without, deproduction of the allyl group using the palladium chloride, followed by carbonate donor generation. It went 2 steps just like that. And then when we tried to do the glycosylation with this one, a variety of substrates, nothing happened. And what we were seeing is simple, the elimination product. That made us to revise the strategy completely. Instead of coming from DE plus F to something like D plus E. At the end of it, people think that ultimately you're doing only DEF trisaccharide. Okay, but let me tell you, ultimately that particular one, when we tried to do this reaction, what we got was this particular orthoester. How much time I have, Satish? Another 5 minutes or 8 minutes? Or I am done?
I think, yeah, you can go for 5 more minutes.
Yeah, okay, fine. Okay, so at that point of time, the student was very unhappy that he could not get the product, the glycoside. But I was very happy because this got activated, first of all. Okay, so, and orthoester 71%, that means that this is getting activated. That is good thing. So then we thought, okay, now let's change the acetate group from here to PMB. Now, because of this PMB, now I cannot have LEV group here. So now acetate has gone, LEV group has to be moved here, and then benzoate has to come. So many cascade of events happened, and then we could get 35%. For the first time, we were very happy to get that particular thing. Okay. And then what happened? Now what I have to do next is I have to continue my synthesis from here, LEV group, and another D moiety has to be added to this. Please remember that. So LEV deproduction in the presence of benzoate has become problem. So then what we did, we put TBDMS here and with a benzoate here. Okay, and PMB, TBDPS with these many orthogonal functional groups, and then we could get 80%. And product and acceptor are at the same RF value without any thing. And now my second problem is deproduction of TBDMS and TBDPS. I mean, I have to deproduct TBDMS in the presence of TBDPS. Okay, which is again yet another problem. So then that made us to move this TBDPS, and benzoate has to be moved here, and then a hell lot of again we do the whole synthesis. Finally, we could get the disaccharide with all these 1, 2, 3, 4 orthogonal. Okay, and ultimately we could get 91% of the yield with the desired stereoselectivity. So once that is done, then the rest of the things have become very cakewalk for us, and we could complete the synthesis in about 2-3 months time. But this required, these 2-3 months came only after 4.5 years of hard work from identifying all the different parameters. And now you see only alpha at minus 40 degrees Celsius, because earlier when we tried to do with the other set, D plus EF, it gave us always alpha beta mixtures, but now we could see only alpha at minus 40. And then we continued to the pentasaccharide, and then we completed that with whatever that DP, we could deprotect each one in the presence of the other orthogonality we used, so that we could get. Now this particular one is also amenable for sulfation, so that we could then get, this is the kind of data that we can, I can explain you much more details and then all that. And then ultimately, if you look at the overall comparison of our route with what is existing in the literature, so we fall, I mean, we believe that our thing is much better than rest of them. The reason is these are all, most of them are solids, and at the same time one can get them as not crystalline materials, but at least as powdery materials. It could be possible that the crystals could be possible. So we know that these are all flexible ones, so one can actually get to whatever combination they want, and then we have all the building blocks, all that. Okay. So overall, last 30-40 minutes, I mean, or more than that, what I could tell you is was all possible because of the great team of students who worked in my group, and then The DST and variety of funding agencies have continued their faith in what we do and then funded very well. I thank all of them. And then most importantly, I thank you all for your kind attention. And I still remain to be wondering what is there in this particular flask, whereas these guys are still enjoying the life out there. Now, these two guys, he has already moved to Bristol, and then these two are now in different stages of the PhD. They have completed the pre-synopsis. They'll be submitting very soon. Okay, with this, I'll close my talk, and then if you have any questions, I'll be very happy to take up. Thank you, Satish, once again. Sorry for overshooting the time.
That's no problem. Thank you. Thank you very much. It's a wonderful talk. Now it is open for questions.
So you can raise your hands, then we can allow you to ask questions. Participant, if you have question, you can put raise hands. And so then we can
click on raise hand. Raise hand means not physically raising your hand. Click it on raise hand in the Zoom.
Yeah.
I don't know, somebody is talking, but we couldn't hear. So I have a question. So is this possible to do on a solid support?
So quite recently, we did that one. I did not include in this particular presentation, but we did the solid phase thing using the Wang resin. And we synthesized a pentasaccharide, and then now we are trying to develop a robotic tool so that it will be similar to what how the solid phase peptide synthesis happens.
Like a DNA or RNA synthesis, that's kind of like
Correct.
same saccharides.
Exactly the same. Similar thing. I mean, the field did not reach to a level of maturity that DNA and RNA or peptide synthesis reached, but I think the progress is towards that one only.
I think it is possible, right? Even making branched oligosaccharides.
Yes, we made in the recent paper that we have published this year in 2022. So we showed that we can use Wang resin to synthesize the same pentasaccharide, penta-arabinomannan, and linear and both as well as branched.
Yeah, in one of your slides, you saw like oxidation followed by reduction. It gave like a stereoselective arabinose monomer.
Yeah.
During the reduction, there is no like enzyme or
no. This is completely by completely by the sterics which play, because this phase is completely blocked.
Oh, okay.
So the hydrate cannot come from here, so the hydrate goes from here. If I want the other way around, then I have to change the sugar here. If I start with the arabinose, then I can get this here, and then I can get the alpha isomer.
Okay, so these protecting groups, benzoyl, O-benzoyl and benzoyl and OR2 are playing the stereoselectivity. Okay.
Yeah, they are guiding the sterics to go. The hydrate can go from that side. Yeah.
From the downside, not from the top side of the carbon.
Correct. For this particular ribose version. So
okay.
Even we did with your nucleosides too.
Nucleosides as well. Okay.
Yes. And we can get, if you know that one, there are 4 pentose sugars. We can get, so that means that 8 isomers will be possible. We can get about 7 out of those 8. Only xylose, if I'm not wrong, xylose alpha we cannot get. Rest of the 7 we can get.
All follows the same method.
All follows. I mean, you change the starting material here. Instead of ribose, you take arabinose, or instead of this one, xylose, you got 2 and then all that. Oxidation reduction.
Yeah, please ask questions.
Someone, Drupta de Jodar.
Yeah, go ahead, ask question.
Did you unmute him?
Yeah,
we have to allow him to ask. Who is that? Okay.
Do it. I don't know how to do that.
Allow. Okay. Yeah. Dr. Deepthi?
Hear me, sir? Yes.
Yeah.
Am I audible?
Yes.
Okay, sir, I had a question regarding this gold. Is it something unique for the gold, or is it this type of reaction can be catalyzed by other metals, other transition metals as well?
It's not true about other transition metals, but there is some alkanophilicity which is available with AU3 and AU1. And it works also with, let's say, something like platinum and ruthenium. But we chose to work with gold because platinum is much more costlier. And on the other side, ruthenium was not performing really well in activating the triple bond.
Okay, sir. Okay. Thank you.
Yeah, if no more questions, now let's conclude this talk at this point, and we will invite Professor Mallareddy for the next talk.
So thank you, Srinivas sir. Thank you so much for these exciting talks. Now we move to our next speaker, the last speaker of today's FDP program, Professor C. Mallareddy from ISAR Kolkata. And Professor Mallareddy did his PhD from HSU, Hyderabad Central University, with the renowned crystal engineer, scientist, Professor Desi Raju. And then he did his short postdoc in Karlsruhe Institute of Technology in Germany. And then he moved in 2008 at ISAR Kolkata as assistant professor. Thereafter, he's promoted in 2019 as a full professor there. He's been doing extremely well in the field of crystal engineering, supramolecular chemistry. And he has been awarded several, prestigious awards. To name a few, he got the Swarna Jayanti Fellowship Award from the DST. And then he has been associate editor from the famous crystal engineering journal Kistinch.com. And today he's going to deliver the talk that adaptive, what is called adaptive crystals from bending to self-healing. So Professor Mallareddy sir, is over to you.
Thank you. Thank you very much. So, can you hear me?
Yes, sir. Yes, sir. You are clearly audible. Yeah. Yeah, we can see your slides too.
Okay.
Yeah.
Okay. Yeah. So first of all, thank you for the invitation, and it's a great pleasure always to interact with you guys at SRM. So I was privileged to visit your campus some couple of years ago, and also it is great to see my very good friend and Professor Hota Srinivas. So and it was nice to hear him. And, these huge molecules and all, really fascinating work. So. I'm going to mainly talk on the molecular crystals. So I will also just show you how we can actually use the crystal engineering concepts to design the crystals which can actually perform certain tasks. Okay, so suppose if you look at crystals, so these are very well organized, and there are many ways through which you can actually design the structure in the crystals, and then once you basically get the desired structure, so then you can also change the properties of the crystal. So my talk will mainly focus on the mechanical properties and tuning of the mechanical properties. And before I go into the details, I will give you overview of crystal engineering, and I will also try to explain what exactly is crystal engineering and how we basically handle the crystal engineering aspects. How do I hide this? Okay. So I am sure all of you know. I think you don't need this slide, but these are all our buildings, and then this is our lecture complex, and this is our research complex, and this is the hostel where most of our students stay. And so materials, if you look at actually the materials, and then materials are everywhere, and then we need very good properties in the materials if we want to actually use them, right? So there are different types of material, and each material is unique to itself, and then it has unique properties. For example, if you look at diamond, and the diamond has some unique properties, and then you look at ceramics, and then they have completely different properties, but they are unique to them. And then you have bronze, right? So then you have spider silk, for example, and then there are many types of materials. So how do these materials, acquire these unique properties? So if you want to understand the properties of the materials, you have to look inside them, and you have to look at their structure. So the structure basically will explain everything about their properties, and then you can, if you understand how the structure correlates with the properties, then you will be able to design the properties as well. This is what we do in the crystal engineering. And then we need to actually understand these properties, because if you understand, then you will be able to mimic some of them. For example, muzzle has excellent mechanical properties, right? So all the work that we do, mechanical work that we do, with our hands or whatever, our muzzles. So that is all because they have some unique structure, and so there is unique organization, and then that helps us actually do all that. So then if we have to mimic this, then we have to go to the molecular level, and we have to see how the energy is transformed, and how basically the self-organization acts on different aspects, and then gives you these mechanical effects. There are a lot of research groups who are trying to understand the different aspects of materials, and then so that we can design. For example, pharmaceutical solids also need a lot of understanding. For example, if you want to make tablets, tablet has to have a very good strength. At the same time, it should have very good resolution, and then it should have very good compactability. You should be able to easily make them. So here again, you need to understand the mechanical properties of the solids that you are using. If you understand, then you can actually go to the molecular level, and then, or you pick the materials that have right crystal structure, and then you can use them, and then you will be able to guide the engineering of these or manufacturing of these processes from the fundamental understanding or scientific understanding. So that is where, so even electronics, like, there are a lot of printable electronics and flexible electronics. In all these aspects, molecular perspective is very, very important. And then you need to understand the structure from the molecular perspective, so that you can also exploit their properties or design the properties in most cases. So again, if you look at pharmaceutical industry, there are a lot of processes where mechanical properties are important. And if you understand the mechanical properties, you will be able to design the powders. This is a very, very important and a big area where people have been working in this area for decades in pharma, because this has a lot of commercial implications. But fundamental understanding on how the particles behave has been missing. And people have been able to solve the problems purely using the empirical methods. So they try 100 different methods. Then one of them works, so they take that method and then go forward. That is how it has been happening in the pharmaceutical industry so far. But now it is a time that we understand the science behind the behavior of mechanical properties of these processes. So that is what we that is where we try to contribute from our research, and we try to understand it from the crystal engineering perspective. And also there are a lot of optoelectronic materials, like organic materials, where you need to understand the structure property relationship. And also the new area which is coming up, which is soft robotics. Again, you need very interesting materials here, and then research groups are actually trying to understand how materials can be exploited for these kind of applications. So here crystal engineering is very, very useful, and it can really help us to basically design the materials. And how do we actually work in crystal engineering? What are the principles, right? So in crystal engineering, mainly you look at the intermolecular interactions. For example, if it is if you're dealing with the organic materials, but for example, if you're dealing with the MOFs or metal organic complexes, then you see you look at how these ligands can be connected with the metals, then how you can actually extend it, and what is the symmetry of these networks that we can form with them. So all that you look at. So basically, you are connecting the molecules or ligands and metals, and to build your entire structure. So that is how we think in crystal engineering. So for example, if you look at actually, so you start from the molecule, and then you basically then you go to the crystal structure, you build a crystal structure from the molecule, and then you look at how these molecules are arranged with each other, or with respect to each other, or how they are connected. So then once you know the crystal structure, then you try to understand the properties of single crystals. Okay, for example, mechanical properties or thermal properties or conductivity properties and all. Then from that, you try to understand the bulk properties, and then you use them for some kind of a application. So that is how we can actually go from molecule to crystal structure to single particle, and that means single crystal. So here you can characterize the properties very well. And then you go to the bulk properties, and then you look at the bulk properties, and then if everything goes well, you might be able to make a product out of it, right? So that is how basically we can go from molecule to product. And so this is how crystal engineering can help. So here, if for example, if you fail to reach here, so you can always modify your molecule and then try to get the right structure, and then try to get the right properties. Then you can go on in the, you keep moving with the trial and error approach. So for example, if you want to build a particular network, okay, how do you build it? How do you use the information from the intermolecular interactions, right? So for example, if you take a carboxylic acid, this is a simple carboxylic acid, this is COOH, right? C double bond O and H. So here, this is positively charged, and then this is negatively charged. And then when you have two such groups, so they will form a dimer, right? So they will form a dimer, and you have a hydrogen bonded network, basically dimer. And then if you know that, this particular interaction is almost always present in most cases where you have carboxylic acid groups. So this is one of the most preferred hydrogen bonding interactions when you have carboxylic acid group in your molecule. So this is the information that you have from the library of known crystals. And then now there are several other interactions, but I'm just taking this particular example. But there are many other interactions which are also very repeatable. Whenever you have those functional groups or combination of functional groups, you will end up with those particular hydrogen bonding interactions. So these are called actually supramolecular synthons. So then, for example, let us take this, and then I am just showing it as a cartoon. Okay, this part I'm showing it, dimer is basically shown like that. And then I take a molecule, right? This is a benzene ring, and then I put these carboxylic acid groups, like this carboxylic acid group in the 1,4 position. So now that I know that these are going to form a dimer like this, and then now I can expect a linear chain like this, where I have carboxylic acid dimers, right? So in the crystal structure, most of the time when you see, so you will actually have these long chains. Then how these long chains pack with respect to each other will again depend on the interaction between these chains, right? So I'm just trying to get you this primary network or primary unit that is further going to pack in the 3 dimension. So if you can predict this, then you can use these hydrogen bonding groups or functional groups and then put them in the right position, and then whatever you want, you can actually design, right? So then, for example, if I keep them in the 1,3 position, then I should also have similar kind of a dimer, what you see here, right? But in this case, it is likely to actually go like a zigzag chain. So here it was a linear chain because I have them in 1,4 position. And here I will have, I'm going to actually have zigzag chains. And then these zigzag chains again will pack with each other. And then, for example, if I actually take 3 of them. So again, what the individual one does is exactly same. So it is going to form a dimer. And then since I have now a 3-fold, so I am actually expected to actually get something like this. So this is how you can predict the supramolecular networks or crystal structure. So then you can basically go on tuning your molecule and then go on optimizing your crystal structure. So once you know how these basically the bigger these networks actually pack with each other, then you will be able to build your 3-dimensional crystal structure. So this is what we do in crystal engineering, and we try to engineer the crystal structures using the intermolecular interaction knowledge or the way the molecules pack. So based on this, basically you can design the molecule. So here crystal structure database is very important, and you look at and then analyze different types of motifs or supramolecular synthons that form in crystal structures, and then use that knowledge and then try to stitch your molecule with different functional groups. Most of the time we take very simple molecules, not like what Professor Hota has shown. So those are very, very complex molecules. But when you have very simple molecules like this, you will be able to actually control the crystal structure, and then you will be able to get the structure that you want. Then, for example, in this case, if we have these hexagons, then you will basically form something like this. And so these hexagons, basically you are going to extend each one. For example, here you have a molecule, this molecule, and it is extended in 3 dimensions. So you get a hexagonal arrow. So these mostly, if you have a big void, either you will have solvent here, if it is a flat layer, or these layers can basically interpenetrate and then actually form more complex structures. So then when they pack in 3 dimensions, so then you get a crystal structure. So then you will measure the crystal structure, measure the properties of these crystals, and then from these properties, you will be able to link them to the underlying crystal structure. For example, if you have layered structures, the mechanical properties from the top and the side will be completely different, and then that you can explain based on the crystal structure that you have in the crystal. So this is how we establish the correlation between the structure, crystal structure, and then the properties. Once you understand what kind of structure is going to give you what kind of properties, then you can go back to your molecule, then you modify it, and then you basically try to build it all the way up to the crystal, and then measure the properties, and then use them for the devices. So this is how basically the crystal engineering works. So for example, if I have to use this group, and then in addition to this, if I use another group, for example, van der Waals group, right? So if I just put it, instead of keeping another same group, so I just keep something else. So in that case, basically, and these groups will not go with this, right? So they don't interact with each other. This is because this is highly polar, and then this is almost like, you know, dispersive group. So in that case, what happens is these groups actually close back simply. Okay, they just try to fill the space, and then since they are of the same type, so they will interact with each other, and then these are van der Waals interactions mostly. And then aromatic groups basically pi stack, right? And then these groups interact again with themselves, and then you get a dimer synthon. So this is how you will be able to build the structure. So since you know that these van der Waals groups are very, very weak, right? So if you have plane in the crystal with completely the weak interactions, so then these crystals are going to be soft. Okay, if we have a dimer here, again carboxylic acid dimer, so it would be more difficult to break these here along this plane than when you have the totally weak interactions like, you know, van der Waals groups. So then if you have van der Waals groups in the plane, you know, in a plane, so if you have a crystallographic plane where you have totally these van der Waals groups everywhere, then that plane becomes very weak. So those crystals actually become softer. So that means if you can take van der Waals groups and then make them pack across a plane in the crystal, so you are going to get soft crystals. Soft crystals means the crystals which are mechanically soft, and then sometimes you are able to bend them, or, you know, you are able to deform them very easily. For example, like wax. If you take wax, then you can basically easily deform it, mold it, whatever you want, you can do it. So crystals also can actually become soft when you have interactions like that, where molecules can move one over the other through the weak interactions. So then what are soft crystals, right? So the crystals which are basically mechanically soft are called soft crystals, and then I will show you different examples. So how did we basically get into these soft crystals? So initially people thought that all the organic crystals, or, you know, for that matter, any crystal basically is brittle, and then they are not very hard like, you know, diamond or something, but they have been known to be very fragile. So that is how people used to think about crystals. But some crystals that we have shown, for example, if you see here, this is a typical organic crystal. When you apply mechanical stress, the crystals simply break, right? So most crystals are like this. So this is a caffeine, one of the polymorphs of caffeine, where if you apply the mechanical stress, simply they break. But then we later found that, you know, some crystals actually bend like copper wire. For example, if you look at it, this is one of the drugs. So if you take these crystals and bend, so they actually bend, and nicely you can mold them into different shapes by bending them. So here what happens is that you have weak interactions here. For example, if you see here, these are CH groups actually. So these are van der Waals type of groups, and then you have weak interactions. And then these are your aromatic groups, which are basically which stack one over the other. And then so then between these stacks you have weak interactions. So when you push the crystal from this side. For example, this is the long axis of the crystal. Crystal is growing in this direction, and then you push from this side. So these layers slip one over the other, and then basically they basically bend. So when they bend, this plane actually here, which is 90 degree here, so it would change to a different angle. The way you see it here, earlier it was something like this. After bending, you will have it. So that is how you can see and explain it in terms of the crystal cracking. So you have weak interactions, and then you bend, then you will have something like this. So I hope this video, this picture makes it much more understandable. So these cups basically sit and then hold each other because of the groove they have, but between these stacks, you don't have very strong bonding, so that is why they can move one over the other easily, but the cups themselves actually hold each other very nicely. So that is what happens when you have stacked columns with weak interactions between them, so you can easily bend them. So this is what we proposed some years ago, and then we did many experiments to show how it works. This is, for example, here it is you have so as you can see here, this is a hexachlorobenzene crystal, so you can nicely bend them, and so this is a plastic crystal. The packing, if you see, you have stacks which are running along this axis, and then between the stacks you have weak interactions as shown here. So then later we came across elastically bendable crystals. In the previous case, once you bend and leave, the crystals don't come back. But then later we found that crystals can also be elastic. For example, if you can see here, so this crystal basically when you bend and then release the stress, so it again comes back very nicely, and so it springs back. So these are called elastic crystals. In case of plastic crystal, there is a slippage. The molecules basically slip one over the other, and the interfacial angles basically change. As you can see here, this is a plastic bending. In case of elastic bending, you compress the molecules, or you compress the unit cells in the inner side, but you are stretching the unit cells on the outer side. So here again, molecules locally basically move, but they don't slip one over the other within the elastic region. So that is why there is a totally different mechanism in terms of how elastic and plastic bending works. But in case of elastic bending, you don't have slip planes. If you have slip planes, simply they would slip, and then you will have a plastic deformation after some initial elastic limit. So there are different mechanisms, but I'm not going into the details of that. So here, if you look at now, there are many examples. So that was first example by us, where we showed elasticity for the first time, extreme elasticity for the first time in organic crystals. And now there are so many examples, and people have been working on different applications and many things. For example, if you look at it, it's here, it's a nice fluorescent crystal, and this is a metal organic complex, and this is also metal organic complex. It is here elastic, this is plastic, and this is here bending is elastic. But this is all, there is also a twist. If you see the molecule, the crystals are actually twisted, right? The twisting is not unwinding. The crystal is not unwinding because it is a plastic twisting. Twisting is plastic, that means it doesn't recover, but the crystal can be bent elastically. So this is very interesting, right? So that here you have thermosalian crystal, where you can see that crystals can jump when you hit them, and this is again. So there are many dynamic crystals, and people have been studying various types of dynamic and soft crystals. So among these, one important class is actually called plastic crystal. So plastic crystal means here, I'm not talking about the plasticity itself. Plasticity means, irreversible deformation. But here, although the name suggests that these are irreversibly deformable crystals, but in these crystals, when you call plastic crystals, so you actually have molecules which rotate in the solid state. So that means you have crystals where molecules actually rotate one or more along one or more axes. So that is why these are called rotator phases or orientationally disordered phases. For example, if you look at here, so you have nicely packed molecules. So they sit in their position, they don't move. You have a nice lattice, and it is highly ordered. But molecules sit in their position, but at their own position, the molecules actually rotate. So that is why they have a dynamic disorder. If you diffract these crystals, you will see that there is a lot of disorder in these molecules. But crystal itself is ordered, and you have long range order, and it is a solid, and diffracts very well, but molecules actually rotate. So these kind of crystals are called plastic crystals or rotator phases or orientationally disordered phases. And so these have some unique properties. And so there is a book actually you can look at if you want. And these crystals are known for some time, but people have not studied the structure mechanical property correlationship in these crystals. So recently we started looking at them. And then we also explained why, how we can actually design some of these crystals. For example, if you look at, this is an ordered crystal, and then as you can see, all the molecules are nicely ordered and then they're nicely oriented perfectly. When you heat this crystal and the molecules actually start rotating, although they don't translate, so in their own position, they start rotating. For example, if you see here, all the molecules are basically rotating. So that means you're going from an ordered phase to plastic crystalline phase. So that means when you have a phase transformation, so you need to give energy to the system, and then it will actually absorb the energy and then go into a different phase. So this is an ordered, and then this is a disordered one. So since you have to give a lot of energy to make these molecules rotate, or ions or molecules or whatever, so then this process actually requires a lot of energy. Okay, so if you look at the DSC, so this peak where you are converting the crystal from order to disorder is is very high. So this peak is very high because you are taking a lot of energy, and then the melting peak is normally in such cases is actually smaller than the order to disorder phase transformation. So why? Because if you look at actually, if the crystal directly goes into the melt, then it attains the rotational degrees of freedom, all rotational degrees of freedom plus translational degrees of freedom. But if you are going actually through this phase, so you already have a lot of energy in the system because your system has very high entropy because you already have these rotational degrees of freedom. That means you put already a lot of energy into the system. And when it melts, what all you gain is only the translational degrees of freedom. That is why energy required to go into the melt here is not as high as when you are directly transforming these crystals into the melt. So here, since you are rotating all the molecules, so all the molecules attain these rotational degrees of freedom in the solid state. So the energy that is required is very, very high normally for this order to disorder phase transformation. As you can see here, so this is a very big jump here. And then in this particular example, this is a different example. So gradually different modes of transformation, degrees of freedom actually are activated in the molecule, in the crystal. So in this particular case, you have a small ion and then a big ion. There are two components. So that is why basically you have different peaks here. But overall, you basically get activate the different degrees of freedom. So since you need to only just rotate the molecules for going from here to here. So normally these phase transformations actually happen from single crystal to single crystal. So this is not very common. Of course, there are many examples. So it is not very uncommon also. But what is important here is in almost all the cases when you are going from order to plastic crystalline phase. So it normally happens from single crystal to single crystal because you're not basically generating a lot of strain here in the crystal because simply the molecules have to rotate in their own position. That is why these phase transformations are very, very easy in that crystals. And then you also have large entropy of fusion but very small in melting entropy of basically fusion. So for phase transformation, you have a large energy. For melting, you have a very small energy. Normally, it is below 20 joules per mole per Kelvin. So kg basically, yeah. So then there are different examples. Like if you have one molecule, normally it is below 20, and if you have two molecules or two different ions, for example, and if only one is attaining the rotational degrees of freedom, so then it can go up to 60. And if both are basically rotating, and if you have two molecules, this can go up to 30. So this we summarized recently in a review. And I'm going to show this particular example where we see a very clear difference between different molecules. For example, all these molecules have basically globular shape. And most of these cases where you see this plastic crystalline phase or disordered phase, you have more or less globular molecules, right? So here all the molecules have almost the same size or same kind of a shape, like globular shape. But here you have 3 methyls, here you have 3 methyls, here you have hydrogens, 3 hydrogens, and then here you have 3 fluorine atoms, right? So here in this case, instead of 3 methyls, you have 1 NH group and 2 methyls. Okay, and then here you have hydrogen. So here, if you compare this with this one, only you are removing 1 methyl and then putting a hydrogen. Since it is highly positive, and then this hydrogen is also highly positive. And since this is negative, and this hydrogen is also negative almost. So then because of this, there is a dihydrogen bonding in this case between adjacent molecules. But in this case, you don't have any strong hydrogen bonding. Intermolecular interactions are very weak, although you have ionic attraction and those are there. But you don't have any strong hydrogen bonding interactions in these 2 cases. And that is why these form these dynamic crystals where you have rotational degrees of freedom, or you can also call them as plastic crystals, but this does not form plastic crystalline state. So if you look at actually here, the melting point of this is actually 94, and here it is 142, and 142 to 146, but here it is only 33 to 36 degrees centigrade. So here you are giving energy to the system, and then basically they don't go into the melt, although they absorb a lot of energy. Simply they start rotating, but still it maintains the crystallinity. But here, once you give some energy, there is no rotational degrees of freedom activated here. So if you just heat it up to 36 degrees centigrade, so these crystals simply melt. So that is the difference. So although they look very similar, so there are large differences in terms of the properties. So these 2 crystals, since they form these dynamic, they have dynamic disorder. So these are very, very soft, and they show very good plasticity. For example, if you take these crystals and then if you press these crystals, you can see that these crystals actually spread, and then that becomes like a thin film. But in this case, it bends on one of the faces. But if you try to bend them in other phase or try to do anything, simply these crystals actually break, because this is not forming the dynamic. This does not have the dynamic disorder because of the molecules don't rotate, because they have strong hydrogen bonding interaction, dihydrogen bonding interactions. But in other cases, they don't have strong hydrogen bonding interactions. So because of that, the molecules actually start rotating the solid state. So these soft crystals, the first 2 basically form very soft crystals, and then you can pull them. And this is very unusual for molecular crystals. You can pull them, you can compress, you can also thin them, and you can also put 2 crystals together and then compress them. Then you also can basically stick them to each other. It is so then this is almost like welding. And you can also take them and then compress. So basically you form a thin film. So you can even rotate, you can even twist, and you can go on doing a lot of things with these crystals, almost like copper at high temperature. You can do whatever you want with that. So in this case also they behave exactly the same. So then we wanted to see if you basically pull these crystals and then take some portion, like you cut some portion and then diffract. So what happens? So we looked at the diffraction pattern, and then we could actually get very nice diffraction pattern from these elongated crystals, and then we could actually get single crystal structure from these cases. And also we could even, after making a thin film like this, around 100-200% increase, in the size, even then when we took a good portion from it and then diffracted it, we could still get single crystal structure from these crystals. This is very, very unusual for the molecular crystals. So then we were obviously interested in the mechanical properties as well as the these plastic crystalline nature, where you have dynamic disorder. So then we looked at this particular example. This is a rhenium, and then you have basically kind of a ammonium type of ion here. So when we form this salt, and we found that these crystals can elastically bend, and then beyond a point they also become plastic. That means initially they are elastic, and then if you push further, so then you have plastic deformation. And when you heat these crystals at room temperature, these are like normal static crystals. But when you heat them beyond certain temperature, as you can see, the crystals actually go into the plastically disordered phase. That means basically crystals, the molecules start rotating after a point, and then it goes into the rotator phase or plastic crystalline phase. And because of that, once it goes into the plastic crystalline phase, then it loses this iridescence. So as you can see here, the phase transformation starts from one side and then it goes to the other side. Once molecules start rotating, so then the crystals also become more isotropic because molecules are not oriented in some particular direction. So molecules start rotating. Because of that, you lose the iridescence in this type of crystals. And you can also take these crystals, heat it to the high temperature, and then press it. Then they become very big. Like you can make them into thin film. And then after that, you cool it again. It retains its. It comes back to its static state, but then it forms a polycrystalline material. So that is what we saw in this particular case. So then I'll go into the last topic, self-healing. So as you all know, molecular crystals are very fragile, and any kind of self-healing is normally not observed in molecular crystals. And because of various reasons, I will explain. Self-healing is mostly found in very soft materials or in biology. For example, if you look at, so this is a bone, the mechanism that I'm showing is actually of bone. So if there is a fracture in the bone, since a bone has also a lot of collagen in it, it's like a composite. And since collagen has polypeptide chains, which is comprised of amino acids, which are basically chiral. So then you have polar arrangement in the crystals, right? So because of that, bone is actually piezoelectric. So then because of that, when you have a crack, and since any piezoelectric material under stress develops basically charges, opposite charges. For example, as you can see in this picture, so when you put bone under stress, so it basically charge separates and one side becomes positive and the other side becomes negative. And similarly, when there is a crack, so it also generates different charges. And then these charges attract the osteogenic cells and which come together and which deposit here, and then they basically start depositing the minerals. So that is how actually it heals. So this is basically a very complex mechanism, but it uses the piezoelectricity. And there is no other example in the literature where basically piezoelectricity is shown to actually help in self-healing. And and there are other examples. And for example, if you look at this is a gel, and where you have polymer with hydrogen bonding, polar groups as side chains. And then in these side chains, you can see that there are a lot of hydrogen bonding groups, and then it forms a nice gel type of material, and it's a very soft gel. And then you take these polymer gel, and then you cut it and then put them together. So they nicely heal. So if you leave them, in a buffer kind of a solution, and then put them together after deforming, so nicely they heal. And so it is very fast also. This is because these hydrogen bonding groups at the crack, where you are basically breaking them, when you put them together in a buffer kind of a solution, so there is a lot of diffusion. Okay, these hydrogen bonding groups can move a little bit because there is a lot of solvent also, since these are gels. And hydrogen bonding groups move, and then again they reform the hydrogen bonding interactions to self-heal. So this is the mechanism in this particular case. And so there are many other examples. I'm not going to show them. Self-healing in most of the known examples requires some kind of a healing agent. Like for example, you need to either heat it, or you have to put them under high electricity or humidity, light, or solvent. Only under those conditions normally self-healing happens in the known examples. And in most of the examples, the diffusion is also very important inside the material. If self-healing has to happen, the material has to be soft, and there should be also diffusion of the material inside the solid. So then only the self-healing happens. So that is the mechanism in most cases. And you need some kind of a dynamic bonds or chemical reactions. There are examples where you can also have some chemical reactions at the surface, and then that basically heals, allows the material to heal. And also it works when broken parts are actually put in contact. If the broken parts are not in contact, so then basically self-healing cannot happen, right? So obviously they cannot come together and heal on their own. So these are the limitations. And then self-healing in crystals is very difficult because crystals are typically stiff and rigid. And as I said, most known materials are actually very soft. And diffusion is also very difficult in crystals because these are more like solid-like, and then materials don't normally dissipate easily, and diffusion is not possible in crystals. Fractured crystals break into many pieces with uneven fracture surfaces. That is why when you put things together also, the contact is not very good, and since everything is rigid, so that's why self-healing is very difficult. And also there are not many examples. That is why people have not studied the self-healing in detail. Maybe it is possible, but people have not studied it in detail, or not many examples are there. That is why it is also very difficult to characterize right now. We need more techniques to develop. So there are only few examples in the literature before our study. So for example, if you look at it, this is an example where you cut the crystal and then put it together for almost 24 hours under some small mechanical compression. Then these crystals actually hold on to each other. And then as you can see here, this is hanging. So crystal can actually hold itself, the other piece. And here, the strength that it regains after you put it for 24 hours is around 7%. So they call it as 7% healing. And this is the molecule. And the other example is, here you cut the crystal into pieces, and then you again compress them under some plates, and then put some pressure for 24 hours. And in this case, it regains about 67% healing. But in none of these cases, the crystallinity was studied at the healed junction. As you can see, the crack is visible. And this is another example where you have a protein with a hybrid polymer, protein and polymer as hybrids, and gel polymer basically. And this crystal, when you put it in solution, it swells. Again, you take it and then put it in a different concentration of the solution. So in a buffer with a different concentration, then it shrinks. So in this process, it develops cracks, and then slowly the cracks will disappear again on their own. So this is also one example. So, but this entire process happens inside the solution, and cracks are also not mechanically generated. So these are basically generated when the crystal basically swells. So we were looking at these crystals from the mechanical property point of view. And my student Surajit, who has just joined as in a postdoc in a different group in US, so he was looking at these crystals. He made this ligand for some other purpose, but since he got very good crystals, so he looked at these crystals. So he found that these crystals are very brittle, and hardness, these are very hard and also stiff, and elastic modulus is around 8 to 15 GPa, and these are highly crystalline. And so since these are highly crystalline, the diffusion is almost not possible in these crystals. But when he looked at these crystals under very small force, like when he just push this crystal, so as you can see here, it develops a crack, and then these cracks disappear on their own. For example, if you look at here, the crack is totally gone. So then we were very surprised because normally in organic crystals you don't see anything like that. And as you can see here, this is a long crystal, and this is a needle, and then you hold it from one side with the forceps. So these are metal pins, and then you're pushing it using a needle. So you develop a big crack, and as you can see, this is a crack. And crystal basically, when you leave it, it comes back and it's sewn, right? So see, as you can see here, there's a big crack and big gap. So, but when it heals, it is very clean. So you can also see here, there's a big crack, and then when you release it, automatically the crystal comes back and then holds itself and then heals properly. As you can see here, the crystals also jump, kind of, there is a mechanical motion. So we didn't know why the crystals are able to come back on their own. So as you can see here in this case, if you break and then put them away, and you push this little closer to this one, and as it comes closer, so this piece basically jumps onto it. So that means there is some kind of attraction here. So we wanted to look at whether there is an attraction. Then we did the KPFM measurements. So here you can actually map the charge, surface charges. And we took a crystal, mounted it, and then we broke this part and created a fresh surface, and then did the measurements. And then we found that, so there is actually a good amount of charge on the surface. Sometimes we found positive charge, and sometimes we found negative charge, because we didn't know the orientation, since these are non-centrosymmetric crystals. So the orientation in the crystal is actually unique, and depending on whether you have it like this or in the other way, so you could actually have either positive charge or negative charge on the surface. So then this tells that there is a charge. And then we took a crystal and then broke it and then put them together. And we measured the crack junction. Then we found that on one side, you have one charge, on the other side, you have the opposite charge. This also tells that at the crack junction, you have complementary charges. So then we proposed that we looked at the crystal structure and studied it in detail. We found that this is a piezoelectric crystal. And since it is a piezoelectric crystal, that means it is actually a non-centrosymmetric space group. And so any piezoelectric material under stress basically would generate charges because you are distorting the equilibrium. And because of that, basically the crystals will generate the separate the charges, like, you will have positive and negative charges. And as you can see here, this is basically a model, and you have a material, and then you push it, and then you deform the shape of the material. And then because of that, you are deforming the also the charges. And then because of that, on one side you have positive charge, and on the other side you have negative charge. And suppose if it is a purely elastic material, and then it will fully recover. And when it recovers, then you will actually go back to this. For example, if it is not a purely elastic material, and then you will leave it in between, so then you will still have some small partial charges. So we believe that in our case, once we break it, the crystal is not fully elastic. There is some kind of fatigue, because of which the charges are still present on the broken pieces, and that helps these crystals to come together and heal. That is what we proposed. For example, if you look at, and these crystals have hydrogen bonded chains, okay, in the crystal structure, and all these have one particular orientation. All of them are actually in one direction, and because of that, your dipoles are aligned in one particular direction. And when you break this crystal, on one side you have heads, and the other side you have tails. So because of that, your basically dipoles are different, and since there is possibly a small plastic deformation or fatigue in the crystal, so then the charges don't go off completely. So that is why there is a small partial, there is a good amount of surface charge, and which basically allows these crystals to combine and then self-heal completely. So then there are different types of applications one can expect. So for example, if you have these plastically or elastically bendable crystals, you can, and if they are fluorescent, for example, you can use them for building optical waveguides, for example. And then, as you can see, this is from Chandrasekhar's group, Chandrasekhar Rajadurai from University of Hyderabad. So they use these plastically or elastically bendable crystals to bend them, and then they make interesting optical circuits, and then you give in light as an input here, then you can basically move the light in multiple directions. So you can make unique circuits to guide the light. And then there are also other groups, we have been studying on different soft robotics applications. So this is actually not a crystal, but all these are also probably possible with the organic crystal. This is an elastomer. So this is from the Metin-Cities group from Max Planck, Germany. So they make these very soft robots, and then these basically these these fibers that you have respond to the light, and then using the light and or also magnetic field, so you can actually make them work. Because of that, you can make different motions in the material. So that is possible, and probably some of these crystals also can be used something like that. And then another group from Australia showed that if you have magnetic, if you have elastic crystals with magnetic activity, if they are magnetically active, and if you bend these crystals, so for a small bend, the change in the magnetic susceptibility will be very high. In one particular example, they have shown in this copper acac. So they showed that very small deflection can actually change a lot in the magnetic susceptibility, and then that can allow you to have high precision mechanical sensing. So these are the type of applications one can have. And then, as I said, in the soft robotics or soft skin or in different types of applications, probably these soft crystals might be very useful. And you can also use these, for example, these dynamic crystals where you have rotatable molecules, and then you can use these molecules for storing energy, or for barocaloric applications for example, these materials can be very useful for the solid refrigerants. So why they are useful. So if you take a static structure and then you give energy, then it goes into the dynamic structure and the molecules start rotating. So you put a lot of energy and then again you give a small compression, then that goes again back into the static state. And then when it goes to the static form, so it will release a lot of energy. So that's how you can basically take the energy into the system and then release it. And you can do these cycles repeatedly, and then that will basically help you to pull down the devices, or in the fridge, the way it works in the fridge. So you can go on doing that, and even perovskites have been shown to work as barocaloric materials. So with this, I conclude, and soft crystals are attractive for various applications. Self-healing in organic crystals is very attractive, but all piezoelectric crystals don't show the self-healing. We need to study them further. And also a lot of biological materials also have piezoelectric nature. So maybe the self-healing that we have shown in single crystals also might have some implications in the biological materials and self-healing thereof. So I thank all my students, Surajit Bunia, who is now with Fraser Stoddart in US. Recently he joined, he did the self-healing work. Amit Mondal is finishing basically his PhD thesis. Saikar is also finishing, and then other people are still working with me. And I thank former group members and postdocs and also collaborators and ISO Kolkata and other funding agencies for generous funding. And Christian Chikam and Dr. B. So if you have nice work, so you can submit here. I am working as associate editor for these journals, and you can always approach me or submit your work. Good work. Yeah. Thank you very much.
Thank you. Thank you so much, Professor Reddy. It is really exciting. It is really exciting talks. And a person like me who never worked in crystal engineering and all, be able to understand. I think it is the same views many of us have. Really thankful. Now the session is open for questions. I can see one question has been posted already by our colleague, Dr. Balaji Babu. Balaji, you want to ask the question directly to the speaker? I can unmute. Let's see, what is Balaji? Yeah, let me read out the questions. Meanwhile, I can unmute him. Hi, Prof. It is nice to see how this plastic crystal bends.
Yeah.
I'm curious to know the reversibility nature of the bent crystals to its original shape. Does it have memory effects? If so, what caused plastic elastic crystals to have memory effect?
Yeah, so the question is about why some crystals are elastic and why some are plastic, and whether there is any memory effect. So basically, see the crystals when you have basically in the straight shape, right? So normally the crystals are straight, and so if you have weak interactions and when you bend the crystal, so in these crystals molecules actually can move like that. Okay, suppose if this is your needle, and if you have molecules. So if molecule becomes like this, then the unit cell actually becomes shorter. If the molecule become like that, then your unit cell actually becomes longer. So on the outer side, molecules become like this, so that your unit cell is elongating in this direction. On the inner side, you have to compress. So there, the molecules actually become like that, so that your unit cell in this direction becomes shorter. So this is the elastic bending mechanism that is shown in most of the elastic crystals that are known today. And so this is simple molecular rotation. Okay, that is what makes them elastic. So here there is no sliding. Since once you rotate the molecules, so you are also putting a lot of stress into the material, and then you're pushing the molecules from their crystallographic thermodynamic positions. So once you release the stress, so then again they will come back. They will move back to their original position. So that is how the elastic response actually works in molecular crystals. So if it is a plastic bending, so molecules normally slide one over the other. Okay, so there is a large movement of the molecules, and then because of that, once molecules move away from their thermodynamic positions, and then the barrier is not very high in this case. So that is why in case of plastic bending, there is no reversible effect. So that is why the molecules actually sit in their new positions, and then they don't come back. So that is how it works. It's not like memory effect, but it is because in case of elastic crystals, you are moving the molecules away from the thermodynamic positions, but you're not moving so much. You're only moving a little bit. So, but a lot of molecules actually move very little. So then because of that, you have the bending. And then once you release the stress, then they will again move back to their original position. Yeah, that is how it works.
Thank you, Professor. I think if anyone has any more questions, you can raise the hands. Meanwhile, let me ask a question. So you were the science paper about the self-healing. So it is a non-scientific question. So can you share with us how did it observe? It is accidental, or we are working on the directions? Can you share the story that will motivate many of us, I believe?
Yeah, see, basically, it was a serendipitous discovery, first of all. And so my student was working with this ligand. So idea was to have a ligand which has both hydrogen bonding groups, strong hydrogen bonding groups, and also methyl groups, a lot of methyl groups, so that you also have van der Waals surface. We wanted a molecule which has both very strong hydrogen bonding interaction groups and then also weak interactions. So we wanted to see, make a basically big network and then see how that responds in terms of mechanical properties. So we were supposed to co-crystallize it with something else. So once my student made this molecule and then he crystallized it and he got very nice crystals. And since he got nice crystals, so he went and then checked the mechanical properties. He played with them. I mean, normally if the student is only interested in the final structure, if the student is not really, excited with the things, you would not have probably gone back and then looked at these, we thought it is useless ligand. He would have just, gone to the final step, right? So since he's like, he's always in a inquiry, right? So he wanted to check the mechanical properties, and then he found that these crystals are actually, jumping back. They come back actually after you break. Initially, we did not see there is a crack and then it is coming back. I mean, so he found that something is happening. The crystals are kind of, jumping immediately and then catching each other. So then he observed it very carefully under microscope. We have a high-speed camera. So he saw it under high-speed microscope, and then he could record this event. And under normal microscope, we could not even see what was happening. It is so fast, actually. This healing happens in milliseconds, and this is the fastest among all known examples. You just break it, and then you release the stress, and you just see the perfect crystal. You don't see if it is a real time, you just don't see anything in between. So he could see that it is breaking, but when you release, then it doesn't see anything when it looks normal. So then he went and recorded it under high-speed camera. Then we could see all these events that videos I have shown. We could see all the events. That is how we basically discovered it. So it is all because student was very curious and he was so involved with the work. And he wanted to look at and observe each and everything that was going around in his samples. So that is how we found this particular example. Otherwise, if we had not looked at these crystals, which were not our final targets, we would have missed it.
Yeah.
That is why if the students spend good amount of time, they're very careful and excited about everything that they see, well, definitely you will get the results. And later, once we had this result, and so then I told the student that this is something very new. I mean, nobody has observed something like that. And then there is a lot of mystery. We did not understand why these crystals were coming back. And we also did not know what exactly was going on. There was no such example, actually. Okay, we had absolutely nothing to fall back on. I mean, this was very different. So then I told my student that, this is very, very challenging if you want to explain what is going on. And you have to read a lot, and you read on this. Then we looked at the structure. We realized that this is a piezoelectric crystal. Then I asked him to read a lot of literature and then see how to characterize a charge. If there is a charge, why they are coming back. There must be some attraction. So this definitely there is no radical or there is no metal, so there is no magnetism here. So then we decided that there must be some surface charge. Then he went around and then checked different techniques that allow you to do the charge mapping. Then we found that there is an instrument in IASC, Bangalore. And then we booked the slot, he went there, and then they also didn't know how to look at these small, very tiny crystals. So in the beginning, they said that we cannot work with this crystal. I mean,
what is the instrument? This is the Kelvin probe microscope?
Yeah, Kelvin probe force microscopy. We never used it.
I never heard it before. First time I'm also hearing that.
It's a kind of a AFM, it's a different version of AFM. I also never knew that such a technique is available. So the student actually found all these basically. I just told him that you have to find something to measure it. So then he looked at the literature and then he could actually plan all these. And then he could do that. So that is how, it was very difficult because we had no knowledge about something like this. So we had to find all the techniques that help us to explain it. So then finally we could actually characterize and then put up a story to explain it. Yeah, otherwise, if you just observe something very unique, of course you can publish it, but if you don't understand, you can always do it in the next paper when there is something very exciting, and it is not difficult to publish it, even the story is not full. But then you will not be able to go to that level. So we thought, okay, this is a right opportunity for us, and then we thought we should take time and then try to understand it for ourselves.
Right.
So that is how we could basically, it took almost like 1.5 years to 2 years for the student to put up the entire story.
Right.
But this was worth the time and effort, definitely.
True.
Yeah.
Thank you so much. Thank you. This is some inspiration for all of us, for all young people, to how to pursue the science. You're a real example. Thank you so much. I think we are almost done, and then I hand over to Dr.
I have a question.
Okay, Satish. Yeah, go ahead.
Professor Mallar. When it comes to amino borons, they have wonderful properties like malleable. They can build, like you can make like a metal, you can stretch, you can make shapes and different. At the same time, when I observe closely, they have the electrical charges. So does these crystals can conduct electricity or heat? Do you guys did any this kind of checking?
So we have not checked the electrical conductivity. These are basically ionic molecules.
Yeah.
Okay. So, and these basically the molecules are basically like, like a tape, positive head to tail arrangement kind of thing. So they form kind of, columns.
Yes.
And then they rotate within the column. And between the column, you don't have any strong interaction. So that is how they are. But I don't think they will be conducting. But definitely they are piezoelectric. Simultaneously, another group actually published the piezoelectricity part. That was also in Angevante. But they could be very interesting, thermal and dielectric properties for these materials, but that is not studied yet. So, yeah.
It's a wonderful talk. So far, I have perception that crystals means brittle, but today I could see all kinds of crystals. It could be plastic, it could be like metal, it could be like anything. So, based on our properties, property of interest, can we go back and design a molecule like a retrosynthesis? Is there any such possibility?
Yeah, it is possible actually. Suppose if you want to design a plastic crystal where you have rotatable molecules, right? So generally what you need to do is you need to take more or less like a globular molecule. Okay, anything that is globular and then has, kind of weak interactions around it. Okay, then it is the barrier for rotation is not very high. So you can design molecule, such a way, and then you can crystallize them and then you can study. So there are certain general principles like this. You can always go back and then try and then see if it works. But it may not work sometimes because you may not understand everything. So your principles may not be right. But
But is there any possible to like develop like it may be beyond like by giving these all inputs kind of like software or something like AI so that it can predict the property that you want? Is there any such?
Yes, it is certainly possible, and there are some groups who are trying it.
Okay.
And I know some people are working on it, but so far there are a lot of groups actually, and there are some people are looking at the bioavailability, dissolution, and then things like that, particularly in terms of the drugs actually. So active pharmaceutical ingredients. So people are also predicting the mechanical properties. Okay, so it is possible, and what you are asking is, whether we can take the database and then look at the properties, understand, and then go back and engineer something which will show some properties.
Yes.
Requires kind of AI or something like that. You need much more efficient technique where the machine can learn itself.
Yes.
Machine learning and AI can basically help here, but people are trying, and nobody has shown really like how you can do it. But there are some, I think there are a couple of examples. people have shown a couple of times. I think there are a couple of examples already. They have a database, small set of database, and then they use the AI to predict back and then design a molecule, and then they have shown that you can actually.
That's wonderful.
But this is very early. I mean, it is certainly possible, and more computational work is required.
Computational energy is needed. Yes.
Yeah. Okay. Professor Malla Reddy said, thank you so much for your wonderful talk and all this discussion. Now I hand over to a request to Dr. Satish to kindly conclude the sessions. So
Thank you, Nimai. Thank you, Nimai.
thank you.
Yeah, thank you very much, both Professor Srinivas Hota and Professor Malla Reddy. It's both are wonderful talks. And thanks for sharing your research as well as your experiences. And I would like to thank our Dean Sis, Professor B.V. Babu, and our Dean Faculty Development, Sudindranath Panda, and our Dean, Associate Dean Sciences, Professor Ranjit Thapa, for their support. And I would like to thank our ITKM team as well, their support. They are the one who arranged all these Zoom meetings. And finally, thanks to all faculty members and students for your presence and making this FTP program successful.